At the end of the talk, you have some stickers here, left over from last conference, if you want to nice stickers. So this talk is not an introduction. This talk is more a dive into group replication, right? So it will be a bit, let's say it's it's not user focused only. It's more like DBA focused and how it works than how to use it, right? First talk, first slide, usual one that you always see this in the Oracle slide decks, right? I'll give you 1 second to read it, and we can start. So let's start our presentation. So my name is Frederic. I am LeFred on Twitter. I'm MySQL evangelist. I'm working for Oracle, and I'm managing MySQL since a long time. I'm living in Belgium, and I have a blog where I'm speaking a lot about MySQL stuff. So if you're interested of everything MySQL, go there, take a look. There's a lot of information, which I try to make some blog posts answering questions or for people having anything you want to do with MySQL. So group replication, what it is. So group replication is the heart of a MySQL InnoDB cluster. So InnoDB cluster is the product, the solution to achieve HA for MySQL very easily. And it uses the router, MySQL shell to orchestrate everything, and group replication. So today, the talk is focused only on the group replication. So what is group replication, right? So group replication is a plugin that is made for MySQL, that is being created by the MySQL engineers, and it is packaged with MySQL. So if you install MySQL 5.7 or MySQL 8, you have group replication plugin already available in MySQL. And so it's all the tests we do, everything, the QA is done, it's all done for the plugin too. So it's an implementation of a theory, and the theory is replicated database state machine. Same. Are there Galera users here? 1, 2, okay. So it's the same theory, but it's another implementation. So this one, it's a Paxos-based protocol. I will go on that later. And it allows you to write on every machine that are part of the groups. So you can write on all of them simultaneously, and it retains it will retain the consistency. It has conflict detection and resolution. The conflict resolution is the first to commit wins, or the first to commit who achieve majority. I will go in details into that later. And it allows you also distributed recovery. So if a node goes out for a while and comes back, it will recover from the group all the missing transaction. It has an automatic failover. This is more in the InnoDB cluster itself, because group replication by itself won't do the routing, but the router that you add in the group replication will do the failover for you if there is an issue on one machine. Automatic membership configuration, so you can add or remove nodes if you have some network failures and stuff like that, network partitioning, all that it's maintained and it's handled in the group replication plugin. Nothing has to be done by the users. It prevents data loss, so this is the goal. So we have two big goals with this solution: is achieve HA for MySQL very easily, and to prevent data loss. Something very important, this is supported on all platforms where MySQL is supported. So it works not only on Linux, but also on Windows, Solaris, OS X, FreeBSD. And it's completely open source. It's GPL. And you don't need any license to have a full HA solution, right? There is no license on that. So if somebody says, oh, this is enterprise only, or if you want to have at least 3 nodes or whatever, you need a license. This is not true. This is full open source and in the community edition also. So it's nice, but how does that work? In fact, this is just a kind of magic, right? This is the magic. And usually we don't explain our magic, but I will try to explain it today. So in fact, the Writeset, I will explain you later what it is. of this, so the replication of the Writeset, so sending all this modification, all this transaction to other nodes, it is synchronous. But the certification and applying of these changes are local to every node and asynchronous. So this is what we call virtual synchronicity. So it's maybe not easy to understand, so I will show you how it looks like, right? So it's not a trick, this is magic. So this is a group of 3 members, right? And you see, this one is the one who is writing for the moment, and you create a DML. This is this is time here. Time is the vertical, and this is a transaction delivery that is made to every node at the same time. If we zoom into that, what we can see is that we send the Writeset to all the nodes, and everybody has to acknowledge that they got the rights to be able to consume it, right? Even the writer has to consume it, because we need to do that in a total order, right? So everybody consumes, even the one who writes. And here, as soon as you have majority, don't forget I said earlier we are using Paxos, right? So here, as soon as we are we're reaching majority, we can continue the process. So we don't need to wait that everybody gets the right set. We have majority, we can continue the process. Then the other one will also acknowledge. When we got all these Writeset sends everywhere, the certification will start. I will come later to explain you just that part, what is certification, right? But as you can see, certification happens when it can happen, right? Usually it happens directly, but there is nothing that says it has to start at exactly the same time, because the machine is doing maybe something, CPU is used or whatever. So when they can, they do certification. When it's certified, the commit is finalized. So here, we go back to the application and say, okay, your commit is done. But you can see, on the other ones, they need to start the transaction, make the changes in the DB on all the pages, and when it's done, the commit is finalized. So if you check the time here, this is why we call virtual synchronicity. This is synchronous, replicated synchronously, but applying, it's not exactly at the same time, because they do it when they can do it, right? I will go into details on that also later. So this is work for auto-commit, but it's exactly the same with several transactions, right? Several statements in a big transaction. This is how it works. Exactly the same. Replication, it's synchronous, and then commit, it's happen when they could happen, right? Of course, this is quite fast, but maybe you are locking the data here or something like that, and that can take time. Okay. So, all the members of the group, they are communicating each other, right? And they communicate through GCS. So it's the MySQL XCOM protocol. It's a protocol that has been created by the MySQL engineers. It do the replication database state machine theory. So this is where it happens, right? It's Paxos based, like I said earlier. This is a variant of Mencius, if you are completely aware of how Paxos is implemented and how it works. So the task of this GCS is to deliver the message across the distributed system. So across all the nodes, they all communicate through GCS. And all this delivery has to be atomic and has to be in total orders for the writes. Right? All the writes, they need to append in the same order. So they receive this order ticket also by the GCS subsystem. So everything that you will write, it all goes through this system. So let's see how it looks like. So this is the basic architecture of group replication. So here are the members. Here, this is the router, but the router can be MySQL router, but it can be also HAProxy, Proxy SQL, whatever you want to use to connect to MySQL. And these are the nodes participating to the group. And this is how it looks like. So a node is MySQL server, is the group application plugin here and this communication between the layers. So let's see how it looks like, right? The plugin stuff here. So we have MySQL. It works only for InnoDB. And then all this is made by the plugin, so the networking it's happening between the nodes. And then you have XCOM, the group communication, so binding all the ports, the API to communicate, the replication protocol, then capture, conflict, applier, recovery, all that is made by the plugin. So the users and the DBA doesn't have to handle anything related to that. So let's take the core now. So here, the plugin API, right? So the server will call everything it has to send to the plugin via a generic interface here. So all these internals are hidden to the plugin and from the plugin or from the users. All that is made in the server. And the plugin will interact also through this generic interface. So, and this is how can we commit, do we have to do all that kind of stuff. It's all made through the plugin, right? I didn't already talk about that, but all this is rely on the very well-known replication infrastructure we know, like binary logs, relay logs, all that kind of stuff. It's based, all group replication is based on that. So you don't have to learn something new. We use exactly the same GTIDs, then asynchronous replication, and the same files, the same way. The only difference is that how we send these events to the group and how we handle them, right? So here the plugin replication, so is executing how we're going to execute all these events, right? And this is a replication plugin that will take care of that, and it will detect and then resolve the conflicts. Resolving a conflict means which one has to go through and commit, and which ones have to roll back, for example, right? The distributed recovery, so if there is, let's say, some node that goes out of network, then needs to come back, stuff like that, all this is the replication plugin that needs to, that will handle that. And for example, if a node goes away for any reason, when it comes back, he says to the group, hey guys, I'm back, this was my last position. Then the group will say, oh, we have already done a lot of transactions since you are gone, so one of us will give you the remaining transactions that you don't have yet, and we open an asynchronous link to it to do this recovery, for example. We also collect a lot of statistics, so all these are done here, and for statistics, meaning how many transactions every node can do in 1 second, for example. And we will use all these statistics, we're going to see in the last chapter, to do flow control. So if you don't know what flow control, we're going to see it later. So it receives all the transactions and define what to do, and then at the end commit or roll back. And finally here, the GCS API. This one is to abstract all the communication between the nodes and the plugin, so the plugin doesn't need to take care of that. And it's mapping all the interfaces because you're going to bind different ports to communicate, and everything is done in GCS. And so all the Paxos implementation leaders and all that kind of stuff is done here. And so this is how the plugin is based in GCS, right? Do you have questions on that? So then is this, I said earlier, we need to apply all these changes in total order, and this is why even the machine that writes need to consume his own write, right? This is to create the GTID. So the group replication use binary logs, relay logs, and of course the GTIDs, exactly the same as asynchronous replication. And there are two ways to create these GTIDs. The first one is automatic. So you don't do anything, and the plugin will take care of that for you, right? This is what the best way to not mess up with your data is to let it do by the plugin. Or you can also assign one. This can also work. So if you have errand transaction, or you have something you want to change some GTID, you can do set GTID next. It will work also in group replication. Of course, this is not recommended but it will work, right? So this is the two ways that you can create the GTIDs. Then we're going to see why they are interesting and how we can use it. So let's explain a bit some magic about the order of the GTIDs. So total order delivery GTID. So here you can see we have a group of 5 nodes, right? And for the best of you, or at least the one with the best eyes, you can see that there is a bit more latency between these 2 nodes and these 3 nodes, right? Here the gap is a bit larger. So we do a commit, and this we send it to the group via GCS, and we do a commit here at almost the same time, right, on MySQL 5, and we send it also via GCS to everybody. As you can see here, we reach these 2 nodes because this one is local, this one is on the same network maybe, and much faster than reaching the other one. And this one will also reach locally very fast, and other nodes faster than this one. So majority has been acknowledged here, right? So the delivery, it means that they say, oh, we got the message already, we can proceed this transaction. So as majority is reached, this transaction will go in the message queue, right? So, okay, we need to process this message, this transaction, and then of course the other one, as soon as majority is reached, they go in the message queue, right? Then everybody will act at the end, but this is the order. So the order was not really the first one to commit in the time, but the first one who was committed and achieved the majority that was acknowledged by the system, right? So then we have the certification to do, and at that time, okay, we take it, say, okay, we can do it. We gave it GTID, the first one, GTID 1. Then we take this one, put in certification, say, okay, this is GTID 2, this one, GTID 3. So this is how we create these GTIDs, why we consume them by order from the queue. Okay? So also, maybe you have seen, but the example here was not totally true, because, for example, these 2 transactions, these 2 Writeset were done by 2 different servers, right? 2 different members. And if you have already a group replication, you can see that we have a lot of gaps between your GTID sets. And this is because we assign big blocks to every node, to every members. So it's not 1, 2, it's 1, then 1,000,001 and stuff like that. So let me show you an example here, right? This is what it looks like, a GTID set. We do a new write on another node. You see, the next write will be a much longer ID. We write on a 3rd node, we have again here. So you have gaps here because the block here it's allocated for 1 node, and the block here from here to 1,000,000 extra, it's also assigned to the 2nd writer, and this one for the 3rd writer. Right? So if you write again on the first one, you can see that it goes in its own block to write that. So this is why if you are using replication with multi-writers, this happens only if you have multi-writers. If you don't have multi-writers, you won't see that. If you use multi-writers, you will see these gaps in your GTID sets. Okay. So now let's take a look at the return from commits. So this is how asynchronous replication is working, right? So we write something on the master, we execute the change, it goes in the bin log, then it sends to the relay log, and here when it's written in the bin log, which is synced there on disk, the return from commit happens. Then on the replicas, we get it's written on the relay log, we read from the relay log, we apply the change, go back in the bin log, when it's from the bin log of this slave, we commit. So this is the return of commit when we use asynchronous replication. When we use semi-sync, so I don't know if you are familiar with semi-sync, who never heard about semi-sync? So you don't know, Marco, what semi-sync is? Liar. So if with semi-sync, when you write in the bin log, you have to wait that a relay, one of the slaves at least, return and acknowledge that he receives the write and he has written it in his relay log. So only then, when you get this act, you can return from commit. This is, you can configure how many you want to wait and stuff like that. Then here it's exactly the same. So the commit is a bit longer because you wait that at least one slave acknowledge that it receives it. Only that it received, not about that he was able to apply it and stuff like that, if there is error or not, that he says, oh, I received it. When we use group replication, and by the default consistency level, because since latest version we have different consistency level, so the default consistency level is eventual. I will go back in details after about all the other consistency levels. This is how it works. So we make a change here, transaction, then we send it to the group, they make the consensus about who, what they had for majority and stuff like that. Then they go in the certification, they're certified. When certification pass, it goes in the binlog, and then it returns from commit. And you see there is no communication between the nodes anymore, just here. Then here we certify, goes in the relay log, we apply the change, goes in the binlog, we commit. Okay. So this is the return of commit when we use EVENTUAL. Now, there is some, you can change about this, this consistency level, and one of them is before. So here, when we write, we wait that all transaction before this one has been executed. So we wait here. When we are sure that everything is clear in the queue, we start our consensus, we execute, and we commit. So before, we are waiting before our transaction that everybody has done everything. And then we have another one, which is after. In this case, we write data here, we do the consensus, we go certify, it goes in the binlog, but after it's in the binlog, we don't commit. We are waiting that the others already prepare and apply the change, and as soon they say, oh, we are prepared, we are ready to apply, they send an acknowledgement and say, you can commit. And then they do also the same. So you are waiting after, so you are sure that everybody has already prepared everything and they are ready for commit. So if we do this, and certainly in EVENTUAL, does it mean that if we have one distant node, because we're always talking about as soon as majority is achieved, I can process. So I can always have this third distant node lagging behind the cluster. The answer is no. Why this? Because we have to wait to what we call the no-op message. So it's sometime we ask to the distant node, so we ask to everybody, in fact, to say, oh, do you have something to say? Right? And then that node, that distant node, have to say, no, I have nothing to say. But we need to wait for we need to pay that latency to ask him and to wait for him about he has nothing to say. So you pay that price, and so more latency you have, even if you never write to that node, you always have to ask him at every time it's his turn to say, do you have something to say? Also, we have to achieve the consensus, we have to ask him, do you have something to say? And he has to reply for us. But we can increase this, the concurrency of how many messages we can have, also waiting before we got the reply. And this is the group replication get write concurrency. By default it's 10. And this is what we call the event horizon window, right? And this is how it works. So this is the group replication write concurrency of 10. This is the window. So we write data here, then it's sent everybody, and then we slide the window. Now we have here 10 writes coming at the same time. Then this one here, another one, a live and write, it has to wait a bit because we have no space left because not everybody acts that it received. So we are waiting for this one to say, I have nothing to say, you can continue, right? As soon as this one says, okay, you can continue, we can slide and we can take this transaction, and again and again. So you can increase this event horizon to 1,000, from 10 to 1,000, not more. Because then if you try to increase it too much, you will break the fact our group replication works in GCS, right? So optimistic locking, conflict. So as I said, we detect the conflict and we take a resolution of it by the first one to achieve majority when it is the first one to pass, right? So group replication use what we call optimistic locking. So by default we say, oh, it will work, and if not, we take action, right? So during a transaction, of course, the local InnoDB locking happens, right? And then we assume that for the other nodes there is no not such conflict happening. So this conflict from the cluster, it happens only when at commit and during the certification. So it's the certification that will take care of this part, and it will happen only if you write on multiple nodes. So let's see how it looks like on traditional locking, so in InnoDB. So we have one transaction on one single node. You start a transaction. Here you see we put a lock on a record that has the primary key 14. Then a second transaction will start, update the same record that is locked. It has to wait that this one commits or roll back before it can continue. This is how it works in InnoDB. So as soon as commit, this one you can go on. Now with optimistic locking, you can see here there is no share locking environment. So we start a transaction and we do another transaction on a second node, and we do exactly on the same record, right? We do some stuff, then we commit, and then we commit here too, right? So this one, if he achieves majority before this one will have at commit time an error because there is a row conflict, and this is the error it will get, right? During certification, you say, okay, this transaction has to roll back because it has been changed by the system. So the conflict certification, it happens on two different stages, right? The first one is only if one of the transaction was sent to the group, and then you locally you consume that transaction, and you have locally already a transaction that conflicts with this one coming from the group. By default, the one from the group has priority, and you will have to roll back your local transaction you didn't commit yet, because this one conflicts and the group has priority. Or if you commit both at the same time, exactly at the same time, they all consume, and the first one that will achieve majority will pass, then the other one has to roll back after that. So this is the error message that you can see. Deadlock form when trying to get a lock, try restarting transaction, or the deadlock retry transaction during commit. So this is the case, the issue you have with group replication when you are doing some duplicate transaction or on the same key on different masters. So this is when they are local, and when they are written both to GCS, the second one get this. The plugin now is GCS that take part, not InnoDB anymore. It's GCS that says, oh, there is a conflict, one has to roll back. Right? Don't forget, these conflicts, they happen only when you are using multi-primary group. So if you write only on one node, it will never happen. If you write on multiple nodes, that might happen. So what are the drawbacks of this optimistic locking if you want to write on multiple nodes? Large transaction. If you have very large transaction, and let's say on another node you just modify one record of this big transaction, if you commit the small one first, you have to roll back the large transaction that was maybe running for 2 hours already. long during transaction, same thing, and hotspot record. So if you modify every time the same record everywhere, you will get a lot of transaction errors, a lot of rollback, because you have conflicts happening everywhere, anytime. So if you are doing one of these three transactions in your workload, you need to write only on one single master, right, and not on all of them at the same time. Don't forget, group replication is an HA solution. You can scale your reads by reading everywhere, but you cannot scale your writes. This is not a scale write solution. The only scale write solution that exists is sharding. You need to do sharding for that, for scaling your writes. Because let's say that the max capacity of one node is to have 1,000 transactions. Every time you write 1,000 transactions on the first node, the second node got this 1,000 transactions too. So you are also to write them this 1,000 transactions too. So it's already at its max capacity. And the third too. So it's not because you have 3 nodes that you will go to 3,000 transactions. Right? So this is very important to know. So this one, it's a long one, but it's a tricky one. Ooh. Consistency levels. So as I said, by default we are using EVENTUAL consistency. This is the default. But since the latest release, we have different consistency levels. So this is how we can work on multiple members and how it works. So this variable, group replication consistency, it's a session or global variable, and the default is EVENTUAL, and you can modify that. And you can modify for some transaction only, for example, if you say, oh, this transaction needs to have a different consistency level. So this is how it works when both are EVENTUAL, right? You are writing, they do what they have to do, and you can do multiple at the same time, everywhere, nobody waits anything, and if there is a conflict, then this one will work back. If not, they will all continue without any problem, but you don't know really when it happened. In this topology, or using this consistency level, what happens? What could happen with this consistency level? Sorry? Yes. Good point, Marco. You won. So yes, here you can have store reads. For example, if you do the commit, if you do this, and you come here, and you read the data, because here, on this one is completely at the same time, but usually this commit might happen a bit later, because it's asynchronous, it's local. You read, so you just write here, and then you say, oh, I want to read here, and you say, the data is maybe not yet there. You don't know that, right? Because there is no consistency level, it's EVENTUAL. It might be there or not. You don't have power to know about that yet. There is a way to use, it's by using ProxySQL 2.0, who can also knows about the GTIDs, but by default you won't see that. But now in 8.16 we have this, we can change that. So before the reads, so what happens here? You start, you do your commit, and then here you say, oh, I want to change from EVENTUAL to before for this transaction, and this transaction may be writing or maybe reading or whatever, and it has to wait that the transaction before him, so this one commits before being able to execute. So if you do that, store reads are gone. You will be only able to read the latest data that has been written to the server, right? So let's say, and you can do it per session, of course, right? So if you have a lot of let's say a lot of writes and small reads, this is the way you can do it. So you don't pay the price writing, and you say, oh, when I will read, I want this data, could not read any stored data, I use before as consistency level. We have a write, so it means in this time, so we do execute, and then, so here we are after for the blue one, right? So it prepares, and after everybody prepare, they all communicate and say, oh, I'm ready to prepare, I've done my prepare, I'm ready to commit, I'm ready to commit. So they are all, when they are all ready to commit, you commit. And then another transaction that happens here has to wait because it's eventual, and he said, oh, but I need to wait because somebody says it's after, right? So I need to wait for it, and then I can execute, prepare, and commit. So this time, you pay the price here, because when you write, you are waiting that everybody wrote before you works. And now if you want to say, oh, but I want to have always the latest data, and I'm sure that when it's written everywhere, every time. I want to be completely sure that all it's in sync, and I got the latest data anytime, anything I do. You can do before and after. So if you do before and after, you pay the price, of course, when you read and when you write, but you always have the latest data available in your cluster, always. This is almost completely synchronous replication.
Right.
Yes?
Right. This is by majority or quorum?
This, everybody.
So if I have 5 nodes, 2 or...
Five of them need to...
Five,
yes. Yeah, you pay the price.
Yeah, you pay the price.
If you want full data consistency, you will pay the price. So this is why, for example, let's say you are a gambling, let's say, business, and you say, okay, people play and stuff, they're nothing. But then when we're talking about the money and stuff, you can say, oh, for this transaction, it will be before and after, because I want that transaction, not somebody just lose $100. I don't want to say that he reads data somewhere else, and that data is not yet, he still has this $100 that he had before, right? So, but you can do that per session if you need. So this was very, people demanding a lot about this, and we changed it completely by what people are used to, and we think this solution is very, very complete and to avoid everything. But you pay the price of the latency in this case. Right? So this is magic. Another chapter for magic is certification, right? So certification has to, let's go, it only has to answer one single question. And this single question is, can the write, the transaction I'm doing, can be committed or not, locally? If I can do it, then it will pass. If not, it will have to roll back. And so we check all the applied transaction, right, that we have, and so everything what happened and what we have in the queue, if there is some conflicts, and this conflict come only from the other nodes. So if you are writing only on one single node, you will never have any certification conflicts. And this is why, by default, if you are using InnoDB cluster, the default is a single primary. Only one machine accepts the writes, and the router will always send every write to that machine, and the other ones are only there in case of there is a failover needed or to read data. Right? It happens on every node independently, and they are deterministic. And the results of this certification is not reported to the group, so it doesn't require any new communication step. And if it passes, it commits Q to apply. If it fails, we need to roll back, right? And this is serialized with XCOM GCS and get the GTID. And the cost is paid on the transaction size, the amount of rows and the amount of key you have. So before I continue, I want to just talk about this writes and Writeset, because I always say Writeset, if you can apply, we need to certify the Writeset. So what are the Writesets? So let's have a look here. So we have a single table, table 1, who has one single primary key, which is ID, so this one, right? And so when we do a change here, so we start transaction and we change the column C for ID2 and the column B for ID3, right? We're going to create, in the binary lock events, this is what we have. We have the before, before and after image, right? And this is a write set of this and the write set of this. So we create an XXHASH64 of the primary keys, and we create a write set that we're going to use to see if there are conflicts or not. So it contains the full hash of the primary keys or all the keys we have, right? And this is so we don't use everything, we just use the hash to see if there are certification problems, right? Yeah. So this is some example, but I have 5 minutes left only. But so you can enable that if you compile yourself MySQL. This message comes from just a print in the code to see what hash is doing. So if you have multiple one before and after, like an update, you have you create several hashes like this. So if you have multiple keys, you will create different hashes every time for multiple keys also, before and after every time. So this is what we use to see if there are conflicts or not. So this is the certification. I won't go to details in this right now. You will have the slides, but this is all it works. So it's always a loop, and this is how it works to see, okay, do we have something to certify? Yes. Is it local? Is it not? Do I need to roll back? All that kind of stuff is done in certification.
Right.
Yes.
So the certification needs to happen on the queue that you store on each single server, right?
Yes.
So if we have one single writer, the certification needs to happen anyhow because we are distributing the rights anyhow. So there is no way, and it has a cost, but we know that there will be only a single writer. So there is no mechanism to say, okay, I'm using a single writer, so I know that that will be
no conflicts.
No conflict.
No.
There is no way to simplify that.
Currently, no.
Okay.
We will be thinking about that. The cost of certification is not high. It's very small because it's just comparing this big key, right? This hash, so it's very fast. Certification is very fast. So there is no need to currently, at least, to change that.
Okay.
So message fragmentation in 8.0.16, we also have this group replication communication max message CIs, and we are able to fragment and stream this. It's more to fragment the message to the other nodes, because when we had a very large one, remember I was saying about that no op earlier, right? If you are taking a lot of time to transfer the transaction, it might happen that we don't get reply from the others fast enough, and then they get evicted from the group. So if you have a very large transaction, it's better that we say, okay, let's fragment it and we send it to by piece to everybody, and then we also in between communicate to see if everybody is there. And when it's done, everybody just pile up this this write set all together. And when it's done, they just process it after. So when the message is over, they say, okay, it's good, now I can process the message. So this is a way to also avoid these nodes going off when you are writing two big messages to the queue, right? Yes? No problem, Mark.
So you are fragmenting that to make it lighter, the transmission of the...
Yes.
Right? But the package is already fragmented at TCP/IP level. So because the frame, the datagram that is already fragmenting by the specific site. So it's not that fragmenting something that is already going to be fragmented and going to apply, double work at the end in fragmenting and reassembling.
Yeah, the reassembling, you don't have any, what's happening in TCP/IP, the plugin doesn't know, right? You don't have any power on that. But the problem is that if you are waiting for this message, why you send that message, you cannot process other messages coming. And then you send a big message, but you never reply to the group that you are sending that message and that you are still alive.
Okay, so it's mainly for internal communication?
Yes.
Okay.
Because if not, when you are processing a very large node, you are doing this, and then the other says, oh, something goes wrong because these guys start a message, it's not yet finished, of course, but we don't hear anything from anybody else or at this moment. And then what happened when there was a lot of these large transactions, sometimes we had group, members that were evicted from the group because it was taking too long.
So if I do a data loop, for instance.
A what?
A data loop, an insert, or a batch insert, for example.
It will be streamed.
Then it will be fragmented and allow the communication to happen, just to avoid this kind of
Yes.
problem. Okay.
That's the goal.
Thank you.
So when there is a problem, there is flow control. So flow control, it's an operation to say, okay, I told you the plugin also sends statistics. It's my last slide. Thank you. So it always sends statistics to everybody and says, okay, this is where I am now. This is what I'm able to process in 1 second. When somebody goes too slow, the others have the possibility to say, oh, let's slow down, but they never stop the world. We slow down a bit less, and always, we never go under 10% of what we are able to do 10 seconds ago, 1 second ago. So, it's a quota that it's happening by default. You can say, I want to disable the flow control, but you never say, I want to block everything if one node has some issues writing data or it's slow, he has disk issues, he has locking, somebody has locked the data, you will never stop the world. So everything continues, but they slow down, right? And this is not the one who, it's not the node that is slowing down that decides that the other has to stop, it's the other one that says, oh, I will slow down because one of the nodes send me statistics and we're not able to catch up with what we are doing. So this is the schema. I will share the slides with you, but this is how it works, and it works via quota because we are over the time. So this is just for flow control, all the settings you can have. So it's not only enable, disable, but here you can enable or disable, but you have the period, last seconds by default, but you can say, okay, I want the quota based on 2 seconds, 3 seconds. The threshold is 25,000, so when we reach 25,000 transactions in 1 second that we cannot do, we will slow down.
Can you go below 1 second? You can, right?
I don't think so.
I don't.
No. So just this is the life cycle of a transaction. So we write data, it goes in GCS, we will do a GTID events, write values when we satisfy everything. Then we write in GTID, we got the GTID, write in the binary log, GTID, it's certified, goes in the relay log, we execute it, goes in the bin log. So this is how it works in group replication. So thank you. Do you have any questions? Marco has already a lot of questions. So who thinks it's cool, this group replication? Who's going to try it? You should try it, it's very nice. And don't forget, tomorrow the CFP will be open for Percona Live. So please submit your talks. I will be part of the one who rates your talks. So if you talk about group replication, you will have a good rate. Thank you.